Alright, so before we move forward, I should have done this first of all. We're going to take a quick detour. I'm going to just run through spherical coordinates. Since our mass is spherical and we'll have spherical symmetry as it's called, we're going to work with spherical coordinates in the spatial sense. So when you parameterize a spherical coordinates, you have x, y, z equals r cosine theta sine phi, r sine theta sine phi, and r cosine of phi. That's x, that's y, and that's z. Where theta runs from 0 to 2 pi, and phi runs from 0 to pi in terms of radians. Where'd my eraser go? My paper towel eraser. We're going to write this line element here, dx squared plus dy squared plus z squared in a flat space-time setting, I guess. It's not really applicable here. We're going to generalize that line element to spherical coordinates. Alright, so we defined our line element as ds squared, the dot, or the magnitude of our, the differential of our position vector. So dr times dr. Well, how are we going to describe in spherical coordinates our differential of our position vector? Well, we're going to assume we're going to be working with an orthonormal basis. So let's say that dr, so in typical Cartesian coordinates, dr equals sum over I dxi times our little crack there. Basis vectors are basis vectors. You sum over that. Well, when you describe a differential, you have to consider a total differential. So when you're changing from x, y, z to u, v, w coordinates, in our case r, theta, and phi, or phi, I don't know how people say it. What? You have to consider it as total differential, considering the change in each of the new coordinates. Equals sum over the u coordinates. Can you see that well? Well, we're going to consider this to be written in terms of an orthonormal basis, k sub u, which is the constant term here, times du times our new basis vectors. So we can remove the sum here. We're going to assume that these new basis vectors are orthonormal, which means when you take the magnitude, there's just going to be 1. So we're going to take the magnitude of this whole thing and cancel out the differential of u equals k sub u, and then we can write equals our basis vectors here. And now, okay, and k sub u is equal to that. Alright, so when we calculate our line element, equals K sub u In a non-orthonormal basis, this would just correspond to a metric tensor. But in our case, we've used an orthonormal basis. We've chosen that. So this is going to be 0. You're summing over all u and v. And this is going to be 0 unless because these are orthogonal to each other. So we're going to set this to, only the v equals u terms will survive. So you're going to sum over u, take that to be k sub u squared. That's just going to be 1 for the u terms. Du squared equals ds squared. And so in the case of our spherical coordinates, we need to calculate each of the ku squared. So that's going to be k sub r squared dr squared plus k sub theta squared d theta squared plus k sub phi squared phi squared. So we need to calculate k sub r, and we already defined that over here as k sub u is the magnitude of the position vector differentiated with respect to u. So in our spherical coordinates, okay, I'm gonna write these up here. This is not very helpful. This is more for my reference, but so k sub r, you're basically just differentiating the because there's just one factor of r for each coordinate. You're basically just dividing the position vector by r when you take the derivative with respect to r. You're taking the magnitude of that. Well, the magnitude, that's just a constant factor you pull out, and the magnitude of the position vector is just r. So k sub r will just be equal to 1. So we can take that. K sub theta will be